Okay, so here are some examples. These are going to be a little bit different because we're not just we're not just computing the derivative, we're actually finding the equation of the tangent line. So to find the equation of the tangent line, well, we're just finding an equation of a line, and we know that to do that, we need to know a point on the line and the slope, right? Find the equation of a line. We need a point on the line and the slope. Okay, so what we know about tangent lines is that, so if our function looks something like this, let's say, and we have a tangent line at, say, this point right here, we know that the tangent line passes through that point. So that's part of the definition, right? So it goes through that point, and then the derivative gives us the slope. So all we need to do is figure out so we're given the x value, so we need the y value, so we just need to plug in 2 to get that into our function, and then we're going to compute the derivative, and that will give us the slope. And then we just use the point slope form of for an equation of a line, right? So first we plug in 2, we get 2 times 2 squared minus 3 times 2, which is 8 minus 6, so this is 2. And so that means if we want to write it in coordinates, that our point is going to be 2, 2, right? Okay, so now we want to find the slope of the tangent line at 2, and that is equal to g prime of 2, okay? And so we set up our limit, right? So I'm going to do the one where we take x approaching that number 2, and then this will be g of x minus g of 2 over x minus 2, right? Okay, now we just plug in, this should be 2. We just plug in the formula for g of x, so that's 2x squared minus 3x, so that's the first piece, and then it will be minus g of 2, but we already computed that, so we'll just write in 2, and then in the denominator that will stay the same. Okay, now what we can do is factor this. So we actually get, I think I can fit this here. If you factor this, you can get x. So you want x minus 2, and then I think plus 1. Okay, so we can double check that works out and gives us that quadratic. So okay, this is nice because now I can cancel this x plus 2 with the x minus 2, sorry. I can cancel those factors, and then we just have a linear function, which is one where we can just plug in x equals 2. So I just plug that in, and I will get 5. In fact, I'll write it right here. Okay, so that means that g prime of 2 is equal to 5. So the slope of the tangent line is 5, and it passes through the point 2, 2. Okay, and now if you don't remember the point slope form, that's the formula where you have y minus y1 equals m x minus x1, where the m is the slope, and then the x1 and y1 are your coordinates of your point. So if we just plug in our coordinates, we get y minus 2 equals 5 times x minus 2. And so if I want to rewrite that, I would get 5x minus 10, and then I move that 2 to the other side, so plus 2. So the formula for the tangent line is going to be just 5x minus 8. Okay. So in the book, if you look in the textbook, there is like a formula for the tangent line. I don't recommend that you use it or memorize it. I think that it's much simpler to just do it this way and use your previous knowledge of finding the equation of a line, because the formula itself is kind of confusing, and I think it's just more trouble than it's worth. Really, just doing this is much more straightforward. Okay, so we have another example of finding the equation of a tangent line. So here it says, find the equation of the tangent line to the curve. Unfortunately, I wrote over this, so maybe I can move it. Oh, took the y with it. Okay. No. Okay, cool. Okay, so the curve y equals 2x over x plus 1 quantity squared at the point 0, 0. So this is given as, it's given as y equals something. So when we have something like this, we usually use the notation, y prime. And so very similar to the f prime of x notation or f prime of a notation, is just to match, the form that it's given in. And so this is at the point 0, 0. So that means that our x, so going from the x coordinate, the point we care about is a equal to 0. Okay, so I know that they're both 0, but if you are given a problem like this and given a point and you want to know, well, what is the point I'm actually looking for the derivative at, it would be at 0. Okay, so let's see. So we're going to compute the derivative, right? Because we already are given the coordinates of the point. And so I'm going to use the formula involving h. So limit as h goes to 0. And that would be of f of, maybe I'll write it out, a plus h minus f of a over h. And here I'm letting be y. So, okay. Okay, so just plugging in the formulas, I will get 2 times a plus h over a, oh sorry, my a is actually, I should do that part first. Okay, so my a is equal to 0, so this is actually just f of h minus f of 0 over h, right? Okay, so now that I've got all that, I just need to use the formula that we're given. Okay, so I would get 2h over h plus 1 squared, and then if we plug in 0, we get 0, which we already know from the fact that this lies on the line, or on the curve. Okay. Now we just need to simplify this. This is a complex fraction. So what we have is an h in or you could, I mean, there's several ways to simplify this, but I guess I'll write it out. We can rewrite this as multiplying by the reciprocal. So we can see this as being h over 1. So the reciprocal would be 1 over h. And then we would cancel, right? Okay, and then we no longer get 0 in the denominator, so we can go ahead and plug in h equals 0, and we get 2. Right? We get 2 over 1, so just 2. And that means that our slope is, so the slope of our line is equal to 2, and our point is 0, 0, so our equation of our line is pretty simple. It's just 2x. Right? So this is the tangent line at 0. Okay, now we have one more example, and this is of a function that's a little bit different, but I mean, we've been doing this, or we've been seeing this absolute value function pretty frequently. So the idea here is that, well, we have f of x is equal to the absolute value of x, which can be written as a piecewise defined function where it's equal to x if x is greater than or equal to 0, and it's equal to minus x if x is less than 0. And then, so what we want to compute, if we want to find the derivative at 0, that would be the limit as x goes to 0 of f of x minus f of 0 over x minus 0, right? Which is equal to just f of x over x, right? Because if we evaluate at 0, well, the absolute value of 0 is just 0. Okay, so this is the limit we're interested in, and we are told, so this would be f prime of 0 is equal to this. We are told to show that this does not exist, so it kind of gives you a hint that you might want to look at the left and right hand limits and show that those are not equal, right? So if we look at the limit as x goes to 0 from the right of f of x over x, now since x is approaching 0 from the right, that means that any value that we might plug in is going to be greater than or equal to 0, which means that the formula we should use is just x. Okay, so that means that when we're computing this limit, we should use the formula just x over x, which simplifies to 1. So this is just the limit of a constant, which means it's just equal to that constant. So it's 1. Whoa. Okay. Okay. Here we go. Okay, and then we can do a similar thing when we're approaching from the left. In that case, the formula we would use since we are approaching from the left is going to be negative x, since all of our x's will be less than 0. Okay, so we get negative x over x, which is equal to limit as x goes to 0 from the left of just negative 1. So since that is a constant, the limit is just equal to negative 1. So we get that the limit from the left and the limit from the right are not equal. So left and right hand limits do not agree. So f prime of 0 does not exist. So this points out something that could happen, which is that the derivative might not exist. So it's defined via a limit, and we know that sometimes limits do not exist. So sometimes the derivative of a function at a point does not exist. And just to like picture this graphically, the absolute value function, it looks like x for x greater than 0, and it looks like minus x for x less than 0. So it's like this corner looking thing. And so notice that if you're looking at this point right at 0, it comes to a point like this. Okay, so let's imagine we zoom in on this, and it looks like a corner like that. And so you can see that if we were approximating from the left, all of our secant lines would be the same line. It would just look like this, just extend this line. And then if we were approaching from the right, all of our secant lines would look like this other line, and they don't come to agreement, because we have this corner right there. And so that's going to be a common thing that will cause a function to not be differentiable at a point. Okay, so hopefully that's clear. Another thing is that if a function has a derivative at a point, there's an idea that if you have basically that the function is smooth, and that so it doesn't have any corners like this, and if you were to zoom in, so if you were to imagine like zooming in on this function like a lot, so you keep zooming in and zooming in, it will essentially look like a line, right? And so actually really close to that point, so we're zooming in around this point on the graph right here, really close to that point, the function essentially behaves like a line. And that is an important idea, I think, when you're thinking about derivatives. Okay, so that's all for this section, and don't forget to complete the comprehension check.